Video 4 of Chapter 3. We are now going to take our scatter plots and we're going to finally apply what you might know as the line of best fit, or what we're going to refer to as the LSRL, to our data set. Now, at the end of video 3, I left you with this important question. What can we do with that correlation value R that gave us the direction and the strength of a linear relationship? We said the stronger the linear relationship, the more useful the data is for making predictions about values that we do not have data for. So with our correlation, we went stat over to calc. We used number 8 linreg and not number 4 linreg. And we put in our lists L1 and L2. And when we calculated, then here's how we got the correlation value R. But I mentioned in the previous video that we would get to talk about the A and the B value. Now, the A and the B represent the y-intercept and the slope values for the line of best fit that best fits this data. And so if I were to look at that data, then here is my line of best fit. Now, we haven't talked about yet how to get this line of best fit to happen in your scatter plot, but we will get there, okay? Now, some other names that you might get for line of best fit, you might refer to it as the trend line, or again, what we're going to refer to it as is the LSRL, which represents the least squares, if I can spell squares right, there we go, least squares regression, nothing like spelling vertically here, line, the least squares regression line. And I will discuss what that specifically means in a future video. Now, here is the equation of this line, of this linear equation here. It's y hat is what we're going to refer to this little rooftop symbol here. So we'll call this y hat equals our y-intercept, which starts at 0.06, and you can't really tell based on this graph here, but it starts up just a smidge, and then it's got a slope of 10.03, rounded to 4 sig figs. So again, y hat is our predicted value. This again is our y-intercept. Here's our slope. And the x is going to be an actual x value. So if we didn't have a value for, say, 4.5 hours of sleep in this particular problem, that we were doing hours of sleep versus test scores, then I could plug in 4.5 for x, and I could come up with a decent prediction for what y is. So here again is 2 ways you can make that particular prediction. You could use your graph, and you could say, well, 4.5 would be in between 4 and 5. And if I were to go up and hit the LSRL, the trend line, the line of best fit, and then scroll over to my y-axis horizontally, then that value would be my predicted value for a person with an x value of 4.5. Now, that's found algebraically just by plugging the 4.5 value into x and then doing this math here. So 0.06 plus 10.03 times the 4.5 gives us that 45.195. And this is predominantly what you guys should do. You should plug values into x, churn out the math here, and then come up with a predicted y value. All right? So could you plug other numbers in besides 4.5 into x? Sure. Really any number you wanted to for x that would really make sense for this particular problem. And you could come up with a predicted value for its corresponding y. Where'd my pen go? There it is. All right. Now, does our trend line make useful predictions? Ooh, that's a good question, because sometimes we could have a trend line that doesn't really make very useful predictions. But since our correlation was so strong, it was almost 1, it is an extremely strong linear relationship, then will this LSRL, this trend line, this line of best fit, will it make useful predictions? And in this case, absolutely yes. I mean, notice our data points. They're not far away from that prediction line, if you want to think of it that way. So if I were to come up with a particular value, say 2.5, then I would think it's going to be right here on my trend line. Now, where is it actually going to be at? Well, if I look at the other points, I'm going to say it's probably going to be pretty close to this line, and I'm not going to be far off from what I thought it was going to be. Now, if we looked at a counterexample here, if I had a really weak linear relationship, so here's an example where the correlation is just 0.2245. And so look, here's my 6 data points in this particular small data set. Here is the LSRL, the line of best fit. And you're going to notice here that I've got 3 points that are above and 3 points that are below. And man, this prediction line really isn't too terribly close to any of these points. So if I were to come up with and say plug, well, not 3, but let's do 3.5. If I were to plug 3.5 into my LSRL equation, I would think the predicted y value would be somewhere around like between 30 and 40. Where might it really end up at? I might get something like, I don't know, like 60. Like maybe that data point is really up here, but I think it's going to be right here. And so there's going to be a lot of error. I'm going to be off quite a bit from what I thought was going to happen versus what really did happen. Now, I'm not saying that that point will be up here. The point for 3.5, if there actually was a data point, maybe it is really, really close. So I'm not saying that this particular trend line is going to make bad predictions, but it's going to make potentially wildly unpredictable predictions. You might make predictions that really do end up being close to the actual value, but you might end up making predictions that are really far away from the actual value. So will this trend line make useful predictions? Maybe, maybe not, but I'm going to kind of lean towards probably not because of that weak strength of this scatter plot. So the ultimate conclusion here is the stronger the linear relationship, the more useful the data is for making predictions about values that we do not have data for. Okay, so I'm not saying that if you have a weak scatter plot that you can't make predictions, because you certainly can. But will those predictions be accurate or mostly accurate predictions? Maybe, maybe not. Okay, we'll start to get in those kind of fuzzy areas like, I don't really know if you can really trust this prediction number. Another example I want to show you here is our line of best fit, the LSRL. It is the best possible line that fits our data, but there are technically infinitely many other lines of not best fit. All right. So you could have some lines like this red line or this pink line. They're really close to the green line, right? Their slopes are slightly different here, but you wouldn't want to use that red line to make predictions when the green line makes the best possible predictions. So I just want you to understand here that there's only one line of best fit, and there are infinitely many other lines of not best fit. But the line of best fit provides the best predicted values. Now, there is a different way of getting the equation of a regression line besides using your calculator, right? So we use that linreg command. We got the a and the b, the y-intercept and the slope from our calculator. There's one other way that involves if you don't have the actual data to put into list 1 and list 2, but if you had some statistics about your explanatory and response variable. So if you know both the mean and the standard deviation of the explanatory and response variables and the correlation between the two variables, then we can figure out what the line of best fit is, what that LSRL represents. So this is a problem where you need to know 5 numbers to be able to accomplish this.
So on the official AP Stats formula sheet, you are given some extra information. And it's not always on the formula sheet from the AP Stats exam are they going to give you every single solitary formula. The z-score formula back from chapter 2 is not officially on the AP Stats formula sheet. That's something they expect you to know and to memorize. And so these 3 things, they're just written on the formula sheet, but you are not given any indication about what they find in particular. So it's not going to say like, hey, this is the formula. Let me get my highlighter. This is the formula to find the y-intercept. It's not going to say that. This isn't going to scream at you, hey, this finds the slope of the regression line. You are going to have to remember those particular pieces. So again, you're only going to see this and this and this, which means this little nugget of information down here is something you are going to be in charge of. Now, let's kind of first break this down here. The generic LSRL format. So y hat, this is our predicted y value. I want a different color here. Let's go orange. This is our predicted y value, y hat, equals a, and a is our, this looks like our ln reg a plus bx format. So this is the y-intercept, plus b, this is our slope. So if we look at the two formulas for y-intercept and for slope, we're going to notice that it uses a bunch of those things back from here, where these are going to be like the givens to you in the problem. Or maybe you would have to use your calculator and do some one variable stats to figure out what's the means of x and y, what's the standard deviations of x and y, and what's the correlation. But typically these are given to you. All right? You just need to know what's the explanatory and what's the response variable. Again, think of explanatory as the cause and the response is the effect. So if we look at the two formulas here, if we first look at the y-intercept formula. So here's the y-intercept, and notice they don't write it as a equals if this is the y-intercept formula. They're making this look an awful lot like the generic format, except instead of writing y hat, they replace it with y bar. So they're plugging in the mean of y into y hat, and they're plugging in the mean of x in for x. And that's true because of this little nugget of information that I mentioned earlier. Every line of best fit contains the point x bar comma y bar, the mean of your explanatory variable and the mean of your response variable. So that means if that point is on the LSRL, this being the LSRL, then that means the x and the y in here can be used with x bar and y bar. Now, that means you're going to know these two numbers, right? You're going to know x bar and y bar, the means of x and y. But to solve for the y-intercept, you need to know b, which is the slope, which means you're going to solve typically for the y-intercept second. You're going to need to first come over here and solve for the slope. So what do we need to know for the slope? We need to know the correlation, and we need to know the standard deviation of the response variable and the standard deviation of the explanatory variable in that particular order. If you flip-flop these two standard deviations, there's a really good chance you're not going to get the correct slope. So first you're going to plug these numbers into your calculator, whatever they may be, and then you're going to get the slope. And then you're going to take that number and plug it in over here, and then you can get that y-intercept. All right? So let's practice one of these together. So is the number of hours studied for a test related to the score that you get? So here are your statistics, your summary statistics for what's going on here. So notice I didn't give you the data, but I told you the average number of hours studied is 1.55 hours with a standard deviation of 1.323 hours, and our average test score was a 79.7% with a standard deviation of 16.06%. And the relationship between number of hours studied and your test score gives us this correlation of 0.8381. Now, we're going to do part of this together, and then the other part I'm going to leave for you, because really it's just plugging numbers in and doing some basic calculations, primarily in your calculator. So first, we're going to, again, need to start with the slope. So we're going to start with this formula right here. And we're going to need the correlation, R. So we're going to be dealing with the 0.8381. And we're going to need the standard deviation of our response variable, which is the 16.06, and the standard deviation of our explanatory variable, which is these number of hours studied, 1.323. So we're going to use our calculator. So this is going to turn into 0.8381 times 16.06 divided by 1.323. Now really, out of these three numbers, we've got multiplication and we've got division going on. And does it matter, according to the order of operations, which one you do first? And no, it doesn't matter. So I'm just going to type in my calculator 0.8381 times 16.06 divided by 1.323 without any extra special parentheses or anything of that nature. So all of this tells me that my slope, nope, it's not equal to, it's going to be an approximate number here. And I'm just going to go to 2 decimal places. 10.17 to 2 decimal places. So there's my slope. So now this is the you do part for you guys. You are in charge of solving for the y-intercept. And remember, you're going to need the slope to help you do that. And we just figured out what the slope was. So you're going to figure out the y-intercept. And then you're going to write the equation of the LSRL, the least squares regression line, the line of best fit, the trend line. So you're going to write what this is, which means once you figure out what the y-intercept is, you pop that number in here. We get to take our slope and pop it in right there. So you're going to have 2 answers in the you do. What is the y-intercept? And what is the official equation of the regression line? All right, the interpretations. We talked about the slope and the y-intercept. Now we really need to discuss what do those numbers mean to this problem. Now, typically when you were in Algebra 1, you probably didn't do very many word problems where you had to interpret what the slope and the y-intercept meant. But now we're going to get into there. And so this is where some people kind of struggle because they don't take the time to actually think about what these values represent. So first, the y-intercept. So in general, this goes all the way back to Algebra 1, but the rough interpretation of the y-intercept was when we would say, well, when x equals 0, if I plug 0 into x, then the y value, but in this case, it's not just any old y value, it's our predicted y value, is going to be approximately whatever the y-intercept value was. Okay, so I'm going to take you back to your Algebra 1 days just real quick. If I had some line that was like y equals 2x plus 1, well, this was the y-intercept, right? And so if you wanted to graph this, you would go up 1 on the y-axis, and the graph would start there, and then you would do the slope, and you'd rise and run, 2 and 1. Well, what this point is specifically saying, that's the point 0, 1, which means x is 0, and the y-intercept is the 1. So it's really the same idea here, but now you're going to have to throw in some context. So we're going to talk about specifically the context coming up here very, very soon with our number of hours studied in our test score. Okay, so just hold on with me for right now. So again, what we're really saying is whenever you plug x equals, or when you plug 0 into x, but make that contextual. When we say, when I don't study for a test, when number of hours studied is 0, then I would predict my y, what's y in context, my test score is approximately whatever it is that you just got in the previous you do part. So this is just going to be kind of a rough interpretation. You need to kind of change out the context. What is x? What is y? What is this value for a? Those need to be actual specific things if I ask you to interpret the y-intercept. And the same thing is going to happen with the slope. With the slope, it has its own interpretation. Remember, slope was defined as the rise over run, or the change in y over the change in x for my calculus people. dy over dx, right? If you're thinking some calculus related stuff there. But we're not going to talk about calculus. Why can't I get my eraser? There we go. So here's the very generic interpretation of slope. Is for every 1 x, whatever x is in context of the problem. Like the last one we were talking about, for every 1 hour I study for a test, we predict y, but what's y in context of the problem, to Now notice I have n/decrease. If the slope is positive, then you're going to say an increase. But if the slope is negative, then you're going to say that there is a decrease. All right, so it really depends. You're either going to tell me increase or you're going to tell me decrease based on the slope being positive or negative. By approximately whatever that slope number is. So in that last example, our slope value was 10.17. So again, we'll talk about specifically what that is in the next part. So I just want to make sure that you get the rough idea of what we mean by interpreting the slope. For every 1x, and you do have to say for every 1x, because I will tell you, there are times that I have graded the AP exam, and I had to grade a problem that was basically interpret the slope. And I would see students write, for every x, we predict y to increase or decrease, whatever it was, by approximately b. And at first glance, I was like, oh, they forgot the word 1. Is that really a big deal? And so I started asking around, and people would say, it is a big deal that they leave out 1. Because if you just say, for every hour studied, by default, that doesn't necessarily mean 1. You know, you could say for every 2 hours studied, for every 3 hours studied. So you do have to put this actual value of 1 in there when you interpret the slope.
We're going to interpret that together to end out this video. So here are my slope and y-intercept values. And this was for hours studied versus test score. So first let's start with y-intercept. Y-intercept interpretation. So again, that was when x equaled 0, then we would predict y to be whatever the y-intercept value was, which in this case is 63.91. Now, I'm not going to say when x equals 0, because I need this to be in context. So what was x in this problem? X was hours studied, and y was test scores. So when a student does not study, now, you might throw in kind of more of a numerical twist into this. When a student has 0 hours studied for a test, but that sounds kind of awkward. So you can just make it sound like what it could naturally sound like. When a student doesn't study, that means there were 0 hours being studied for this test. We predict, and again, this is the important part, we predict, we're not coming up with an actual y value here, but we're coming up with a predicted y value. We predict the student to score approximately a 63.91%, assuming these test scores are in percentages. So when a student has 0 hours studied, we predict the student to score approximately a 63.91. Now, could that be possible? And if you think about it, could a student not study and have 0 hours? Sure. Could the student really score a 63.91%? And you might go, I don't know, what about that 0.91? Is that really going to be possible? Well, theoretically, yeah, that could be possible. But there might be some times where you would say when a student doesn't study, we predict the student to score like -5%. So that's a theoretical, okay? Let's say the y-intercept was -5. And you might go, but I don't think a student could score -5%. Or what if the y-intercept was like 112? And you'll go, when a student doesn't study, we predict the student to score 112%? Well, how did the student get over 100%? That's not possible. So there are some times where the y-intercept might not literally make sense to that problem. But in this case, this y-intercept does make sense. A student could not study and actually get a score of 63.91. Sure, that's possible. All right, now let's do slope interpretation. Now the slope was this 10.18. Well, I'll go 4 sig figs again. And we're going to say for every 1x, then we predict an increase or a decrease in y of whatever the slope was. So for every 1x, but I'm not going to say for every 1x, it's for every 1 hour studied. So for every 1 hour studied, or if you can make that sound less robotic, you can. So for every 1 hour studied, we predict, don't leave out the prediction part, we predict, and in this case my slope was positive, so we predict an increase of approximately, then what was our slope? 10.18% in the test score, in Y. Test scores was Y. So what we're saying is for every hour studied, you would expect a student to score an extra 10% on their test. Now, this is going to have some limitations, right? You can't say if a student studied for 10 hours, hey, 10 hours at 10% per hour, that's 100%. Man, you study 10 hours, you're going to ace this test, I can guarantee it. Well, if you study 10 hours seriously, you probably will ace the test. I mean, you've put in a lot of work here, right? So this is really saying that the more you study, the more you're probably going to get a better grade, which should be true in general. So there's our interpretation of the y-intercept and the slope, and we'll definitely get some more practice with this. But the only problem you guys need to do, again, was going back and figuring out the y-intercept and really writing the whole line of best fit. And that is all for video 4.